Building on the foundation of simple interest, we now have the opportunity to study compound interest. Did you know that Einstein called compound interest a miracle? It is a wonderful phenomenon and an excellent way to grow an investment. It's related to simple interest, but it is different. In a simple interest investment, money is added into your account once per year. Interest is paid once per year. However, with compound interest, which we're studying in this section, interest is paid multiple times per year. For example, let's suppose that you have a basic compound interest savings account that pays interest quarterly. That's 4 times per year. And at the beginning of the year, you deposit $100. Well, after the first quarter, which will be after 3 months, you're going to earn interest on that $100 that you deposited. Then for the second quarter, you're going to be earning interest not only on your original deposit of $100, but now on the interest that you earned from the first quarter. So compound interest builds interest upon interest. This causes your principal to grow faster, and again, it is the best and most excellent way to grow an investment. We will examine both the compound interest future value formula and a present value formula. Let's look at the future value formula to begin with. The future value of a compound interest investment is given by A equals P times 1 plus R over N exponent NT. Now compare this to our simple interest future value formula. This one is a little more complicated. Some of the variables are familiar, but we have a new variable called N. Let's review what all of these variables represent. A is going to be the amount in the account, also known as the future value, what the account is going to grow to. P is the principal, the amount invested. R is the rate of interest, and we've learned by now that always has to be in decimal form. And T is time in years. All of those variables are the same as they were in the simple interest future value formula, but what's different about this formula is N. N is the number of times interest is compounded, and compounded simply means paid, and this is per year. So again, whereas simple interest is paid once per year, compound interest is paid in times per year, and that can vary from different banks and different investments. This is a fundamental formula upon which many of our formulas we'll study later in this chapter, such as an annuity saving for retirement, or even the payment that you make on a car or a house is related to this formula. So it's a very fundamental formula. Now let's see how this formula works, and let's get a feel for how a compound interest investment is different from a simple interest investment. Example 1. Find the future value for a principal of $1,000 at 2.1% for 5 years if interest is compounded annually, semi-annually, quarterly, or monthly. So these are some various options out there for different compounding periods. Notice our principal here is $1,000. The rate is 2.1%, and we're going to convert that to a decimal by moving the current decimal left 2 places. 5 years is the term of the loan, or the time of the loan, and that's given in years. And so these words here describe N, the number of times interest is compounded per year. If interest is compounded annually, that means N equals 1. Now, let's write down our compound interest future value formula here, and let's plug in our variables. We're looking for the future value. We're trying to determine A. of $1,000 at 2.1, which would be 0.021, compounded once per year. So I'm going to plug a 1 in for n here and a 1 in the exponent position. T is 5, so in that exponent position we have 1 times 5. Now if we simplify this just a little bit before we plug it into our calculator, we end up with 1.021 to the 5th power. This investment is equivalent to a simple interest investment, which pays interest once per year, but this formula is going to calculate the future value of that at the end of 5 years. So let's type this into our calculator and see what the future value of our $1,000 investment is. So I'm going to type it in exactly as it appears, written by hand. When I'm ready to enter the exponent, I'm going to use the caret key there above the divide button. And then I'm going to enter the exponent 5 and press enter. So it looks like our future value is $1,109.50. So $1109.50. So this is a one-time lump sum deposit at the beginning of the term. We deposit $1,000. We leave it alone in the bank and let it grow. At the end of 5 years, it will have grown to the future value of $1,109.50. So we earned $109.50. Now let's compare that to the next example. What if interest is compounded not once per year like simple interest, but twice per year? Semi-annually means twice per year. So I'm still using this same formula. I still have the same principal and term, same rate, but we're going to change our n value. So this is going to look like 1,000 times 1 plus, the rate r is 0.021. Now for the n, I'm going to plug in a 2 here, and in the exponent position we have n times t, or 2 times 5. Now I'm actually not going to simplify this one. I'm just going to let the calculator do all the work. I'm going to type it in exactly as I have it written by hand. So we're going to type in 1,000, open parentheses, 1 plus 0.021 divided by 2, close parentheses. Now we're ready to enter the exponent, so we're going to hit the caret key, and we're going to multiply 2 times 5. Our investment will grow to $1,110.10. Remember, we round money to the nearest penny. That is the nearest hundredth or the nearest 2 decimal places. So $1,110.10. So notice by compounding twice per year, we earned just a little bit more than compounding only once per year. It's not a big noticeable difference, but it would be a bigger noticeable difference if our term were a little bit longer, if it was a long-term investment. Okay, let's see what this would be for a quarterly compounding. That means interest is added 4 times per year, or every 3 months. So everything in the formula is going to stay the same except for the n. We're going to change the n from 2 in the last problem to 4 in this problem. So in our exponent, we're going to have 4 times 5. So the only thing that changed was the n value. So I want to show you a shortcut that you can do on your calculator. Now previously I've typed in the formula with n equals 2, and the only thing I need to change is n from 2 to 4. So I'm going to press my second key and then the enter button. Notice above the enter button it says entry. That's going to recall what you just typed in. Then you can use your arrow keys to navigate through your entry. I'm going to get right on top of that n. I'm going to change those 2's to 4's. Okay, so same formula, I'm just changing the 2 to a 4, and then we can evaluate. Notice with this one, we earn about 31 cents more. So $1,110.41. $1,110.41. So hopefully you're starting to see that as you increase the n value, that increases your investment. That can make a big difference over a long-term investment, such as saving for retirement. Let's look at saving monthly or compounding monthly. If interest is compounded monthly, that means N is 12. So the only thing we're going to change in the formula, once again, is the 12. We're going to change the N from 4 in the previous formula to 12 in this example. So I'm going to do the same shortcut, second entry, but we're going to have to handle this one just a little bit different. I can type over the 4 with the 1. I want to enter a 12 here, but if I enter a 2, it's going to take the place of that asterisk. So I'm going to have to do second insert and then the 2. That'll give me enough character spaces to write the 12. I'm going to do that here as well. So I'm going to type in 1, second insert, the 2. Now, if you just want to retype the whole thing, that's also a valid option. Give you a little more practice plugging it into your calculator anyway. $1,110.61. So at the end of 5 years, if I left that $1,000 alone, that means I'm not withdrawing from it and I'm not adding to it, then the interest that I would collect would be $110.61. So the higher the compounding period, or the higher the number of times interest is compounded per year, the bigger N value, the greater the future value. Now, also, if you add to your principal by making regular deposits, that also causes your principal to grow, and your investment then grows even faster. We're going to examine that in the next section. That's called an annuity, and it's based on this fundamental formula that we're doing here. Let's do a compare and contrast formula. Number 2, calculate the future value of each of the following savings strategies. What was the total cost of each investment, and which strategy is a more efficient way to save money? Okay, so you're planning for a long-term investment. You're going to start saving money over a long period of time, which is an excellent and wise decision. Example A, or strategy A, says you're going to deposit $25 per month every month for 25 years. That's pretty doable. $25 a month every month, and you're going to make that a habit for the next 25 years. Let's figure out the future value of this investment. So this is not a compound interest investment. This is not a simple interest investment. You're just depositing money into an account. So $25 per month, that's 12 times per year for 25 years. Let's see how much you would end up with at the end of those 25 years. So $25 per month for 25 years. You would end up with $7,500. $7,500. Okay. What was the total cost of the investment? Well, I deposited every single bit of that future value, right? The $7,500, we didn't receive anything from interest. So the total cost there is $7,500. This is the future value, and it is also total cost. All of that came out of my pocket, right? Okay, let's compare that to strategy B. You're going to invest $5,000 at 4% compounded monthly for 25 years. Do you notice how this one's different? In strategy A, you did this every month for 25 years. In strategy B, you're going to make a single one-time lump sum deposit. Okay, so this is a single one-time lump sum deposit. Okay, maybe you have an excellent tax return one year, or maybe you have some sort of insurance settlement, or maybe you have some sort of inheritance, and you decide to take this lump sum and you're going to put it in the bank at 4% compounded monthly. So that means N is 12 times per year, and you're going to do this for 25 years. So since this is a compound interest problem, I'm going to use my compound interest future value formula. The principal here is $5,000. The rate as a decimal would be 0.04. N is 12 because interest is compounded 12 times per year. And we're going to do this for 25 years. Okay, we're going to leave it alone for 25 years. Let me say it that way. Let's see what the future value of this investment is going to be. So we have $5,000 times, just going to open parentheses here, 1 plus 0.04 0.04 divided by 12, close parentheses. I'm going to type the caret to get in the exponent position, 12 times 5. So this investment would grow to $13,568.83. $13,568.83. So the total cost of this investment was how much came out of our pocket. We deposited that $5,000. But notice our future value is $13,568.83. Did I remember that correctly? $13,568.83. Okay. Back up here on this first strategy, all $7,500 came out of our pocket, and we did that every month for 25 years. We didn't deposit into either simple interest or compound interest. We just set it aside. So the future value is $7,500. Notice it is less than the future value of our compound interest investment. Also notice that it costed us more for that investment than the second option, right? $7,500 came out of our pocket in strategy A, but in strategy B, this higher future value only had a present value. It only costed us $5,000. So you can start to see, or at least have a glimmer of understanding of why Einstein called compound interest a miracle. It is a very wise and efficient way to save money. The smaller amount that you contribute is made up and more in the interest that you earn. So this one would be a better, more efficient savings strategies. So if you don't have a savings account, now would be a great time to open one, find a bank that offers quarterly or monthly interest, and start saving money.